So what Jodrell Bank's been all about for more than 60 years now is exploring the invisible universe. When you go out at night and you look up at the sky, you're using your eyes to look at things there. You'll see stars, you'd see the moon maybe. If you're lucky, you might see something like a comet. And for thousands of years, that's what we were limited to doing, was just using our eyes. About 400 years ago, Galileo first used a telescope. And what the telescope does is it lets us get an enhanced view of things out there in space. So it collects more light, lets us see fainter things, magnifies the view. But visible light, the sort of stuff that your eyes can see, is not the only sort of information that's coming from space. It's only one part of a huge wide spectrum. It goes all the way from radio waves at one end, through infrared, then the visible, and then out beyond that you've got ultraviolet, X-rays and gamma rays. And these days astronomers would use every bit of that spectrum to get us different information about the universe. And the first bit of that spectrum to be opened up outside the visible to allow us to look at the invisible universe was the radio part of the spectrum. Radio waves are they're what's called electromagnetic radiation. They're all part of this big wide electromagnetic spectrum, from radio waves at one end to gamma rays at the other and visible light in the middle. And the difference between these different types of radiation is what's called the wavelength. They're actually made up of electric and magnetic fields that vary, and the distance between the sort of peaks in these fields, that's called the wavelength. And the wavelength of visible light is very small. It's maybe a millionth of a metre or less. But the wavelength of radio waves is much longer, maybe a few centimetres, 20 centimetres, maybe even a few metres. So it's the wavelength that's the crucial difference between radio waves and visible light. Radio astronomy actually began back in the 1930s. Karl Jansky, who's an American engineer, was studying radio waves as part of a task involving, using radio waves for terrestrial communications. But he found a source of radio noise that he realised was actually coming from space. So he was the first person to pick up radio waves coming from outer space. Another American called Grote Reber, later in the 1930s, built his own little radio telescope in his back garden actually, and he was the first person to start to map the radio sky. Here at Jodrell Bank, observations began in late 1945, and so we were some of the first pioneers of the new science of radio astronomy. So here at Jodrell Bank there's actually 4 radio telescopes. There's the big Lovell telescope, 76 metres in diameter. When it was built it was the world's largest radio telescope. It's still the 3rd largest steerable telescope. There's another large telescope on site called the Mark II telescope, and together those two work as part of a network of telescopes across the UK. We call it Merlin, which actually combines 5 remote telescopes with the 2 large ones here. That acts as a giant telescope spanning the whole width of the UK, gives us a sort of magnified view of what's up there in space, a sort of zoom lens if you like, lets us look at details. And then there's another 2 smaller telescopes here at Jodrell Bank. One spends its life looking at pulsars, the dead remnants of exploded stars. They're basically ridiculously extreme objects that weigh about as much as the sun, but they're only about the size of a city, and they spin in some cases hundreds of times a second. And one of the other telescopes, the other small telescope, is actually used for teaching, where we look at hydrogen atoms largely in our own galaxy, and we can sort of measure the spiral structure of our own Milky Way galaxy using that. The main problem we have operating radio telescopes is the wind. If the wind gets up and a big dish is tipped over and the wind blows into that dish, then you actually could risk blowing the whole thing down, which you wouldn't want to do. So we have to monitor the wind speed, and if the wind gets up you have to tip the telescope, point it straight upwards and park it, and that's the most stable position. The other issue would be maintenance, in the sense that radio telescopes can be used 24 hours a day. We can observe during the day, we can observe during the night. In principle, if it's not extreme wind, you could use it all the time throughout the year. Pretty soon it would start to break down. So we do have to factor in periods of maintenance where we look at the structure, we do sort of essential jobs like painting work and so on. The major discoveries that we've made here with the radio telescopes, one of the first things we found was looking at the study of these things we call radio stars, which are these really bright radio sources, and it turned out that many of them, when you say pointed an optical telescope in that direction and you thought, well, what are we looking at here? Is it a star? Is it a galaxy? Is it a planet? There was nothing obvious there in an optical view. And it took some time before the nature of those things was really worked out. And here at Jodrell Bank we pioneered a technique of taking radio telescopes, moving them farther and farther away from the big telescope here, but combining the signals from the two using radio links. So we actually sent the radio signal from the remote telescope back to Jodrell Bank, and by moving them farther and farther away we actually zoomed in more and more detail, and we were able to show that these objects were incredibly tiny. And as it turns out, these things were what became known as the quasars, the distant galaxies with supermassive black holes. Another major area of work here has been pulsars. They were first discovered by Jocelyn Bell with a radio telescope at Cambridge in 1967. They're actually, when they were first discovered, they're this sort of repeating radio signal, as this neutron star, this spinning neutron star rotates, it flashes much like a lighthouse, and so you get this sort of repeating, very periodic, flashing, pulsating signal, hence the name pulsar. When they were first discovered, there was a slight concern maybe that actually we discovered signals from extraterrestrials, so the first one was called LGM1, Little Green Man 1. Pretty quickly it was realised that it wasn't that, it was these dead remnants of exploded stars, and the telescope here, the Lovell telescope here, turned out to be ideal for studying them. So that's been a major area of work here ever since, and we've discovered many hundreds of pulsars, including recently a double pulsar, two pulsars orbiting one another. It's actually provided us with the best ever test of Einstein's theory of gravity, general relativity, showing that Einstein's at least 99.95% correct. We're hoping at some point to prove him wrong, but anyways, at least 99.95% correct. Another major discovery were things called gravitational lenses. These are, it's an effect that was predicted by Einstein with his theory of gravity, where light is actually bent around massive objects. So the mass of an object curves space-time, and that means that light gets bent around it. And the way a gravitational lens works is that when we look out at, say, a distant quasar, and in between us and the quasar there's a galaxy, a source of mass, then the light from that quasar is bent around it, and you can get multiple images of that distant object, much the same way as if you look through your bathroom window, which has got the sort of rippled glass, you'll see distorted images of things out in the garden. We see distorted images of things out in space by the mass that's curving space-time in between us and the distant object. So gravitational lenses were discovered in 1979, and perhaps one of the most fundamental things that comes out of radio astronomy is the fading glow of the Big Bang. We believe that the universe began about 14 billion years ago in the Big Bang, and it's been expanding ever since. Galaxies are flying farther and farther away from each other. But when we look out into space, the farther away we look in space, the farther back in time we can see. And actually the most distant light, and therefore the oldest light we can ever see, is actually something called the cosmic microwave background. It's light that set off in the universe just a few 100,000 years after the universe began, and it's been travelling through the universe ever since. But when it set off, it was sort of dull orangey red colour. The universe was at a temperature of about 3,000 degrees, and so it was glowing a sort of dull orangey red. The universe has expanded by about a factor of 1,000 since then, and so these light waves were sort of stretched to longer and longer wavelengths until now they're in the sort of microwave radio part of the spectrum. And so we can use radio receivers on board on radio telescopes or on board spacecraft like the Planck spacecraft, and we can study this fading glow of the Big Bang and look right back in time, right to very near the beginning of the universe itself, and actually study the origins of stars, galaxies, and in fact ourselves.